Hi everyone. I was hoping to make this a little bit interactive, so if you, in a few points during the presentation, if you dare to try and respond to one or two questions or got some ideas, then either switch your mic on and or have a go on the chat so I can see. So rather than just me talking to you and you just sitting there listening. Anyway, we'll see how it goes. So as Nadine says, my name's Dave Green. I'm a retired physics teacher and a bit of an amateur astronomer. So the advantage of being retired is you can start doing things that you really like to do and didn't have the time to do while you were working. So this chat's about how do we know the distances to stars and galaxies. So I'm just going to start with something called the Hubble Deep Field view. Right, you need to enable my screen sharing for a start, Nadine. Can you do that?
Danny, can you enable screen sharing, please?
Okay, thank you. Okay, I just need to select the right screen. Here we go. Right, so if I put that on. So hopefully what you can see is a picture of, it's a galaxy. Galaxies are islands of stars, which usually have billions of stars in them. This one is estimated to be about 100 billion. Our Milky Way galaxy, the one we're in, it's estimated anywhere between sort of 2 to 3 or maybe even 400 billion stars. So that's a lot of stars, stars being just like our sun. But of course, our sun's very close, so we see it as a disk, but every other star in the sky is a very, very long way away, or sometimes stupidly long way away. So we're going to try and understand how we work out distances. How do we know these galaxies are a long way away and so on. So just to blow your mind a little bit, perhaps to start with, some of you may have heard of something called the Hubble Deep Field photograph, and it was taken by the space telescope called the Hubble telescope, which most of you probably are aware of. Once it was fixed, it's provided some amazing, absolutely still provides amazing views of the universe. And somebody persuaded the controllers to basically point Hubble at an area of the sky that didn't seem to have much in it, and do a long exposure. And I think the exposure was something of the order of 2 weeks. So if any of you use cameras and take exposures, imagine opening the shutter for 2 weeks and gathering as many photons of light as you can. And this is what they saw. So basically this is called Hubble Deep Field. And most of the dots on that diagram are actually galaxies. And some of them you can see sort of spirally things and more diffuse blobs. So this is probably something called an elliptical galaxy. This one here is clearly a spiral, very much like our Milky Way. And most of these are galaxies. Now, a few are stars in our own galaxy. So we're kind of looking through our own stars to the universe beyond. So that one there would be a star in our galaxy, a sort of reddish star, and there's a sort of bluey white star in our galaxy. But most of these are blobs of galaxies. They then did something called the ultra deep field. So they looked at this area here, which appears to have nothing in it at all. And lo and behold, in that area, there's yet more galaxies. And it's like one very, very, very faint star on the previous diagram that's in our galaxy. So the universe is just packed full of these galaxies that we know now are millions or mostly billions of stars, and it's just blows your mind when you think about it. So if I just unshare here, and if I take my I'll take my background off as well. There we go. So what I was going to do, as I say, was to try and go through how do we know the distances to these stars. So the first thing I was going to show you was a lightning strike. So if I the question I was going to pose, and if some of you know the answer, it'd be good for you to put something on chat, or if you like to unmic and you can give me your ideas. But have you ever seen a lightning strike? Quite often, well, there's sort of old wives' tales or sort of rules of thumb of how to find the distance to a thunderstorm, how far away it is. So the question I'm posing really is how do you know the distance to a thunderstorm? So let's just play a thunderstorm. If I share screen again, and just try and find the right. Okay, seems to be. Let's try that one. So I don't want that one. I want this one, and let's have a look at this lightning strike. So I hope you can hear it.
That was nice. That was nice.
Okay, so my question therefore is, what did you see, and how would you work out the distance to that thunderstorm? So I don't know if anybody's got any ideas. We haven't got many on the. Oh, we've got a few more joined. So has anybody got any ideas? Would like to share their thoughts of how you would find the distance to that thunderstorm?
Isn't it where if you basically, however far in the gap of time in between the lightning strike and the sound of the thunder is, depends on how far away it is?
Yeah, absolutely. Well done. Can you just say a little bit more about how you might work out the distance? Because you're absolutely spot on.
Well, say for example, if the lightning and the thunder happened at the same time, it would be really close. But if the lightning happened first and then like a few seconds after, or even a minute after or whatever, the thunder happened, it would be really far away.
Yeah, spot on. So the way you actually work it out, in terms of how many meters or kilometers is it away. If I share my screen again, and we'll put on the PowerPoint. Share that one. Sorry, I'll get better at this. So this is my main sort of set of slides. So how can we measure how far? As you say, if it's further away, the thunder you'll hear the thunder much later than you see the lightning strike. So rather than use like a big tape measure or something, what you need to know is you need to know a speed and you need to know a time. And as you said, if you can measure the time it takes for basically the thunder to reach your ears, then you can work out the distance to the lightning strike. And the reason you can do that is that lightning strike is where basically a big electrical spark from cloud, and it ionizes the air, and it produces a big pressure wave of sound through the air. But of course the light travels much faster than, how do I move my slides on? There we go. So the light travels almost instantaneously to your eyes because it's traveling at 300 million meters per second. Whereas the sound, the pressure wave that's produced by the lightning, is much slower. So it's kind of chugging along behind at 330 meters per second. So essentially, if it's several kilometers away, the light reaches your eye almost instantaneously, within microseconds. So you really better measure that. And the sound arrives at your ear so many seconds later. So if you, for example, let's just go to the next one. No, go back. I don't know, to go back. There we go. So if it was 5 seconds, I don't know who was brave enough to actually try and answer the question, but if it was 5 seconds before you heard the thunder, how far away was the lightning strike? Anybody want to have a guess at that one?
Would it be like 5 miles or something?
Why do you say 5 miles?
Well, if it was like 5 seconds after, wouldn't it be? Isn't each second like a mile or something?
Okay, absolutely good thinking. It's not a mile, but it's 330 meters, because sound is traveling at 330 meters or thereabouts a second. So you're absolutely right in terms of the method. It's just it's not a mile, it's 330 meters. So if it's 5 seconds before you hear the thunder, then the lightning strike was about 5 times 330. So 1,650 meters, 1.6 kilometers away. So every second you count is 330 meters. So basically what I'm trying to say here is that in order to work out a distance, if you have a speed and a time, then that will give you a distance, or can give you a distance. And that's one of the principles you can use to start to work out how far away things are. So for example, how far away is the moon, or how far away is Venus, or how far away is this rock that was imaged by a radar system. You know the speed, so we know the speed of light and the speed of radio waves, which are just like light but a longer wavelength. So we know that they go very fast. They go 300 million meters per second. So we know the speed, and if we can measure a time, then we can work out a distance. I might skip the Big Bang Theory episode, but if any Big Bang Theory, if you like the Big Bang Theory, there's a great episode where they bounce a laser, which is what this is a diagram showing, a laser off a mirror on the moon, and they receive a very faint echo pulse coming back, and using a bit of electronics, they can measure the time it takes for the laser beam to get to the moon and reflect off the mirrors that were left by the Apollo astronauts. I think particularly the Apollo 11 landing site had a mirror. So basically, you can very accurately, to within centimeters or even less than a centimeter, measure the distance to the moon. It turns out the moon is gradually, I think it's something like 4 centimeters a year, on average, is getting slightly further away from us. And we know that because we do this laser ranging kind of measurement. So echoes is a good way. But of course, that's really only going to work if things are relatively close and you can detect the echo. And somewhere, so we have bounced radio waves off Venus, for example, and I'm not sure about Mars, but very, very powerful radio wave, and just detecting a very faint echo, and you can work out distances to relatively near things in our solar system. But beyond that, we're struggling. You can't kind of fire a radio wave at a star, wait for many years and hope to get an echo back from the star, because the stars are just too far away. So we need another method, and that method is something called parallax. So now, I don't know if anybody's got 3-dimensional glasses with them, but you can look online and Google 3D images. So here's a 3D image of Mount Sharp on Mars. And if you have a pair of those red-blue glasses and you look at these images, they appear 3-dimensional. So I don't know if anybody's actually tried that. There's a few more here. So when I do this presentation with people in a room, one day maybe, or something similar, then I give them all a pair of glasses and you can see the 3-dimensional image. So I don't know, does anybody want to go back? Anybody want to guess how the 3-dimensional image appears 3-dimensionally in your eyes, just looking at those photographs?
Is it something to do with what the lens is made of?
That's a good thought. It's not. Can you see on the diagram? Tell me what you see on these pictures, rather. in terms of the red and
Well, actually, with on my computer, I'm just seeing the picture of that really zoomed in galaxy right now, so I can't really see that diagram.
Okay, so that's because didn't stop the share, did I? Right, thank you for that, because I appear to have messed up my sharing. So let's go back. Right. I don't know. So can you see that now?
No.
Okay, so what are you seeing on your screen?
I'm seeing that really zoomed in image of space with all those galaxies.
Okay. Right, I need to stop that. I need to stop that somewhere then, somehow. How do I do that? Right, you'll have to bear with me, because obviously I've done something to stop the sharing of the right thing. So why am I not? Okay, so if I get rid of that, does that disappear? Is it still there?
To share it.
I'll reshare it again. Okay, let's try again. Right, are we seeing something different?
Yep.
Can you see, does it say North Ray Crater Apollo 16?
Yes.
Yeah.
Right, okay, thank you, sorry about that. Okay, so I'll rewind slightly, because you missed, it would have been a bit odd. So I was talking about echoes, so that was the slide you should have been able to see. When I talked about bouncing a laser pulse off a mirror on the moon, and that's a way of, if we know the speed of the light and we know the time it takes for the echo, we can work out the distance, but that's only going to work for nearby objects. Can't do that for stars, because they're a long way away, and you wouldn't get any sort of echo anyway. So these 3D images that I'm just flicking through now, can you see those? There's the comet 3D image. Not that you can see them in 3D unless you have glasses. So the question was, what do you notice about these 3D images? Perhaps I'll stick on that one.
They've got red bits on them.
Right. Can you see the blue bits?
Yeah, just about.
Okay, so what's happening here is that there's two images superimposed, and there's a red image, or reddish with some grey sort of blended in, I suppose, because the comet is basically grey. And then there's a blue image, and they're superimposed. But the red image is slightly shifted compared to the blue image. So you're getting, if I look at that one, for example, perhaps that might be the best one, which is Mount Sharp on Mars. You can see the summit of Mount Sharp is the red bit, the red image. Mount Sharp is to the left. And if your computer screen shows it, there's a sort of bluey, turquoisey bit, which is more to the right. So what's happening when you put red-blue glasses on is you get the red filter on the glasses. The red image comes into your left eye and the blue image comes into your right eye. So your left eye sees Mount Sharp in this example slightly to the left, and your right eye sees it slightly to the right, and your brain goes, whoa, I'm looking at them at slightly different angles, and sees it as three-dimensional. And that's called parallax. And the easiest way to do that is if you hold your finger up, do that now, I'll do it, and you look at the wall in your room or outside the window or something and focus on an object. Look with your right eye shut, i.e. with your left eye, and then open your right eye, close your left eye, and you'll see your finger will appear to shift. Okay, so it's a sort of shift because you're looking at your finger with your left eye at one point, and with your right eye you close your left eye, and the finger appears to move. and that's called parallax. So what we can do is we can use basic trigonometry to work out a distance. So can you see that? Check you're following me on these slides. I've got a slide called parallax here.
Yep.
Yes. Yeah, yes would be good. Yeah, thank you. So so this is an image that's attempting to show left eye, right eye. Instead of left eye, right eye, looking at slightly different angles and getting a three-dimensional image, which is how we kind of perceive distance. So we judge distances because we have a left and a right eye, and left eye, right eye, they're looking at say a ball coming towards you that you're going to catch. The image of the ball is with the left and the right eye looked at slightly different angles, and your brain learns to perceive a distance, work out a distance, or estimate a distance. So we can do the same sort of thing with the Earth. So the Earth, say on this slide, say in August, could be like your left eye. And then 6 months later, there's the Earth rotated around the sun, the opposite side of the sun. That could be like looking with your right eye. And if you're looking at an object or a star, or in this case, for example, the Pleiades, this is the example here, it's a star cluster, then the cluster appears to move against a background of much further away stars. So it's a bit like your finger appears to move against the background of a wall or something when you close your left eye and right eye and looking at your finger. Now this angle that it shows here is called a parallax angle, and is really, really small, as you might imagine, because the stars are very, very, very long way away. But we can measure the parallax angle for nearby stars. So here's an example. Can you see that jiggling?
Yep.
Yeah. So this is an image taken 6 months apart of a patch of the sky, and just basically showing you the two images superimposed, just going between the two images. So a bit like a GIF. And you can see the stars jiggling. So do you want to, anybody else, but is that Ricky or Josh perhaps, whoever's talking? If the star is jiggling a lot, do you think it's nearer or further away?
Is it further?
Why
or
do you say
nearer? I think it might be nearer.
Yeah, you're absolutely right, because the closer the star, the bigger the jiggle, because it's the parallax angle is bigger. If we have a look at the parallax angle again, so if the thing you're looking at and trying to measure the distance of is closer, then that parallax angle is bigger, and the object appears to jiggle much more. If it's much further away, the jiggle, if you like, the amount it appears to move 6 months apart is much, much smaller. So measuring these angles gives you a distance, basically with simple trigonometry. So if you know your soccer tower, you could use tangent, for example. Tangent of the parallax angle equals the distance between the Earth and the Sun divided by the distance from our solar system, the Sun, to the object. We know the distance Earth to Sun. I won't go into that now in terms of how we did that, but again, we used something called trigonometry, and the first time it was more accurately done was using something called the transit of Venus back in the 19th century, I think it was, or maybe in the 18th century, and using some trigonometry, some basic mathematics, and some very, very careful observations from different points on the Earth. They measured a difference in terms of the transit of Venus, and were able to work out the distance from the Earth to the Sun. Now we know the distance Earth to the Sun very, very accurately now, and with that distance and the parallax angle using tangent, tan, you can work out the distance to stars. So there's a lot of words on this slide, but basically what this is saying is that parallax, the parallax angles are extremely small. And in fact, the limit on the Earth of measuring a parallax angle is around something called, the astronomers use angles called arc seconds. So if you imagine a circle is 360 degrees all the way around. So just a tiny way around that circle would be a degree. And if you split that degree into 60ths, you get a minute. And if you split one of those minutes into seconds, you get a second called an arc second, which is basically 1/3600th of a degree. So you can see they're really, really small angles. And due to the limit of the Earth's atmosphere, basically, because it causes things to wobble, the best measurement you can get from an Earth-based telescope is something like 0.01 of an arc second. And that means we can measure stars out to around what's called light years. So I haven't really explained light years, but light years are, because these distances are huge, so rather than say, 11 billion meters or something, some very, very large number, astronomers use something called light years just to keep the numbers a bit smaller. A light year is simply the distance it takes light to travel in 1 year, and it's around 9 billion meters, I think, or kilometers, I can't remember. You can easily work it out. So light years are used as a distance measure, and they are, even 1 light year is a stupidly large distance. And we can measure using parallax around 300 odd light years away, stars that are relatively close to us. Now, satellites up above the Earth's atmosphere can get rid of the wobble, and there's one up there now called Gaia, and it's so accurate that it's doing effectively a Milky Way galaxy survey, and it can measure angles as small as, well, you can see on the slide, tens of micro arc seconds, which is a ridiculously small angle. And that gives you distances of stars, sort of tens of thousands of light years, which is basically, we're mapping with Gaia a lot of our galaxy in terms of how far away those stars are, and it's also able to, by doing repeated measurements, get an estimate of how fast the stars are moving around the galaxy, galactic center. So using parallax, we can now measure things that are in our own galaxy, even going almost like halfway across the galaxy. We can measure by using satellites, using this parallax method, which is kind of amazing when you think about it. So standard candles. So just to recap, we can measure stars that are relatively close to our sun using this thing called parallax, using basic trigonometry and some very accurate measurements. Oh, by the way, I'm skipping through some of this because it's I'm going to run out of time if I'm not careful. But just to give you an idea of parallax, if here's the Earth, and if I imagine the camera that I'm sort of looking at, and here's a telescope, very large telescope. And if I find the UK, here we go. And of course, the Earth's tilted, so it's a bit like that. So if I look at the camera, so the camera is a star that I'm trying to measure the distance to. Well, 6 months later, the Earth's kind of gone around the sun, and my telescope is now pointing miles away from the camera, and I have to tilt the telescope kind of like that until I'm now pointing at the camera again. So that amount that I have to slew the telescope, that is going to give me the parallax angle. So that's essentially how it's done. Okay, so that was a quick demo there. So, but parallax only works for relatively nearby stars. So the idea of standard candles, I'll just put a curtain over here, is that you measure when you look at stars. So here's a candle, but imagine it's a star. And here's another candle, not a real candle, it's one of these little battery ones. Okay, so here are two stars, but apart from the actual size, can you tell me what else you see different between this star in my left hand and this star in my right hand? Can anybody tell me any other difference? This one looks bigger. Anybody want to have a stab? Oh, there's some chat. Sorry, I haven't been looking at the chat. The right-hand one is darker. Yeah, well done. Sorry, I should have been looking at chat, shouldn't I? Okay, so this one here is fainter or darker, and this one here is brighter. So actually, you can use this to estimate distances. Essentially, light spreads out from, like in this case, this little candle, in all directions over a sphere. And if you know your area of a sphere, it's 4 pi r squared, where r is the radius, or the distance. So if this one here is twice as far away, it should be about a quarter of the brightness, if they are the same brightness to start with. So if they're the same brightness, I move this one twice as far away, its brightness will drop by about 3/4. So it'll be about a quarter of the brightness, because the light is spread out over a much bigger surface area. And as the surface area is related to the square of the radius. So if you double the radius, 2 squared gives you 4. So basically the brightness goes down by a factor of 4. And if you triple the radius, the distance, it will go down by a 9th, and so it'll go down to a 9th, and so on. So if you can pick stars that are basically the same brightness, but you view them and one is much fainter than the other, you can work out, especially if you know the distance of this one, say you know the distance of this one using parallax, this one here is too far away to use parallax, but if it's the same brightness star, you can look at its brightness and think, oh, it's about a 9th of the brightness of this one, therefore it must be 3 times further away. And that's called the standard candles method. Okay, so if I know the distance of this one using parallax, because this is a nearby star, and then this star is much, much further away, we know they're the same brightness. I'll explain how we know that in a minute if we choose our stars carefully. If we know this one and it looks about, let's say, a 16th as bright as this one, and we know therefore that this is about 4 times further away than this one, and therefore we now know the distance of this one because we know this one from parallax. Okay, so that is called standard candles. How do I know the same brightness? Spot on. Yeah, good question. Sorry, I haven't been using chat properly, have I? Why am I getting a message saying 3 minutes to go? My talk is an hour. Is that right?
Yeah, so your talk is about 45 minutes, 50 minutes, just to give the next person a chance to hop on.
Yeah, sorry, I was getting worried. You were counting me down. But okay, so we know they're the same brightness. So let's go back to share. I'll go back to my slides, hopefully. Share. Can you see that? Back to our standard candles slide. Yes?
Yes.
Thank you. Okay, so essentially using standard candles, if we know a star is 500 light years, here's an example from a parallax measurement, and another star looks 16 times less bright, then it's about 4 times 500, it's about 2,000 light years away. Okay, question on chat was how on earth do we know that some stars are the same brightness? Really good question. And it's all down to a variable star called a Cepheid variable. Now, basically Cepheid variables, this is a graph that might blow your mind a bit, but basically it's saying that it turns out by looking at nearby Cepheid variables that we know the distance from parallax. Somebody called Henrietta Leavitt, and she was really completely instrumental in our understanding of distances to galaxies, because she did some studies of Cepheid variables that we knew the distance to by parallax, and she drew a graph basically of a variable star as a star that just varies in brightness, and it regularly varies in brightness over a period of a few hours or a few days. And by knowing the distance to a whole load of Cepheid variables and measuring the periodicity of their brightness going up and down, she was able to draw a graph that basically showed there was a linear relationship between the brightness of a Cepheid variable and how quickly it varies in brightness, its periodicity of brightness. So this gave Hubble, an astronomer in the 20th century, the means to work out. So there's Henrietta Leavitt. She's the lady who did the work. And basically Hubble observed Cepheid variables in one of those fuzzy patches that 100 years ago astronomers thought, well, they're just fuzzy patches in our own Milky Way galaxy. He measured some Cepheid variables using a very big telescope. So he needed a big telescope to actually see individual stars in what we now know as the Andromeda Galaxy. And he measured their periodicity. And therefore, using Henrietta Leavitt's graph, he knew what their actual brightness was. But then seeing how faint they really were in his telescope, he was able to then work out the distance. And it turned out that the Andromeda Galaxy was millions of light years away. So it was a separate island universe. Okay, so there's a picture of the Andromeda Galaxy on the left there. Just for fun, I've shown a picture of what's called a barred spiral galaxy, which is what our Milky Way looks like. This is obviously not a picture of the Milky Way because we can't get outside the Milky Way to take a picture of it. But this is what we think the Milky Way looks like. And our sun is somewhere in a spiral arm towards the edge. And that little blue dot represents how far radio waves have actually gone or got over the last 100 years. So it just shows you how big these galaxies are. But anyway, this Hubble was able to measure this distance to the Andromeda and realize that they were separate island universes. But of course, some of these galaxies, you looked in the Hubble Deep Field view, those splodges, then you can't identify individual stars, even with a really humongous telescope. So there is a limit to how far out you can go. So there's another standard candle that's used. It's called a type 1a supernova star. So it's a special type of supernova where it's due to a white dwarf circling another star and sucking the material off the other star. It gets to a certain size and physics tells you how big it can grow before it blows up into a supernova. So those type 1a supernova, by knowing and understanding the mechanics, if you like, or the physics of how the star and the supernova forms and explodes, we know the absolute brightness of these type 1 supernova. So if you see a type 1a supernova in a distant galaxy in your telescope, you know what its absolute brightness must have been, and you can see how faint it is in your telescope, and then you can work out the distance. Okay, so spot the supernova. No, I'm not sure this one's going to jiggle, but there is one of these blobs, and these, it might be that one, is the supernova. This pair of galaxies, which you can view in a pair of binoculars, actually in the constellation of Earth's the Big Dipper, Great Bear, is quite well known because it's doing lots of stars. Lots of stars appear to be dying. It's had several supernova in the last 10 or 20 years, so it's quite a quite worth a look if you've got a big telescope, just to see something, if something's appeared. Okay, so I'm getting towards the end now, because essentially the last sort of piece of the jigsaw, if you like, is that we can measure distances to galaxies, certainly relatively nearby galaxies, by looking at Cepheid variables, and we can also use type 1a supernova to estimate distance to the galaxies. And what Hubble did was he looked at the light from these galaxies and measured something called redshift. So basically he measured, I'll explain what redshift is in a minute, but he measured this thing called redshift of these galaxies, and he realized that the further away the galaxy, which he determined using Cepheid variables or type 1a supernova, the further away the galaxy was, the bigger the redshift. So basically the redshift is related to the distance the galaxy is, and indeed it's related to the speed with which the galaxy is going away from us. Redshift means the galaxy is moving away. So he's able to draw or do this kind of analysis where you can measure using this thing called redshift how fast the galaxy is moving away from us, and you can relate it to the distance, which you know using Cepheid variables or type 1a supernova, and it turns out it's on a straight line-ish. So there's a sort of a relationship. And what that meant was, if you can measure redshift of even more remote galaxies, you know their velocity away from us by doing some simple maths. You can use this graph to estimate the distance. The other thing Hubble realized from these redshifts was, of course, they are all redshifts, and basically redshifts means, okay, I don't have time to do the demo, and that's about diffraction, but I'll move on to this bit. Redshift basically means that when you look at the light from a galaxy, the light tells you a lot about the gases that are in the galaxy. And the most abundant gas in the universe is hydrogen. So if you look at the spectrum of hydrogen, these are called absorption spectra, but essentially use something called spectroscopy. And you can look at the lines that are produced by excited hydrogen gas. Those lines appear to move if the object, the galaxy that you're measuring and looking at and using spectroscopy, those lines, if the galaxy is moving away, appear to shift towards the red end of the spectrum. So essentially, if you look at this middle one here, these lines compared to measuring where the hydrogen, these are called hydrogen absorption lines, where these lines are, say in a lab on Earth, it isn't moving away from us. Here might be a galaxy that is moving away from us, and we're looking at the hydrogen absorption spectra, and they're shifted towards the red end. They were shifted to the right here, to the red end of the spectrum, and that's called redshift. Okay, so what Hubble was able to measure was that a lot of these redshifts he was measuring showed that most galaxies are moving away from us, and that was the first evidence that the universe is expanding. And as I said before, even more, that the further away the galaxy, the bigger the redshift. So by measuring redshift, you can estimate the distance to galaxies, and you can get right out to, you know, very, very large distances. So redshift is the I won't go into that in great detail. Redshift is the sort of mainstay way of actually measuring how far away the really remote galaxies are. So here's a summary. believe it or not, it's only in the last 100 years really that we've realized that our Milky Way is just one tiny pebble on a huge beach of galaxies in our universe. I guess Brian Cox would say at this point, it's billions and billions of galaxies or something, some big number. And dedication scientists like, I say, Henrietta Leavitt really unlocked the key, or had the key, unlocked the means of realizing that our galaxy is just one of billions. It's just amazing how we now know a lot more about the universe that we live in. But there's a hell of a lot more to find out. Like, do we live in a multiverse? We know there's stuff called dark matter, but we don't know what it is really. And even weirder, there's something called dark energy. So if anybody on the call wants a challenge, then there's a lot more in astronomy yet to know. Okay, I guess I'll stop there. Yeah, I've got 9 minutes, so 2 or 3 minutes, I suppose, for questions. If anybody's got any particular questions, I unfortunately did rush through the redshift thing, but if you're doing A-level physics, then you'll learn about redshift. Certainly, if you're doing OCRB, there's quite a lot on redshift in there, and it's all based on something called the Doppler effect. Has anybody got any questions? Is there anybody still there?
How close is anyone to actually finding out what this dark energy stuff is?
Oh, not very, I would say. There's, if you, especially on YouTube, there's some really good YouTube channels that you can look at and discuss these kinds of things. Dr. Becky Smethurst, I think her name is Dr. Becky, is a fantastic channel. If you're really interested in astrophysics, then go on YouTube, search for Dr. Becky, and she's doing her she just finished her PhD. Yeah, she's just finished her PhD. But she goes into all sorts of things, including, dark matter, particularly. I think she talks about, I'm not sure if she's done one on dark energy, but the short answer is miles away. We don't know. Lots of theories, but no real evidence of that might back up any theory at the moment. Okay, any other questions?
What do you think dark energy could be?
Oh gosh. Well, I'm absolutely not an expert. I mean, there is one theory called the multiverse, which I quite like, but that is almost like no way of proving it. Science goes forward based on evidence and observing stuff and supporting a theory and bolstering a theory perhaps, and maybe making predictions and going off and observing something to see if it is right. A multiverse, which the theory says, well, we 100 years ago only thought we were just, well, you go back 300 years, we thought we were it, Earth at the center of the universe, sun and planets go around us. Then we realized that's not true, it's the sun, we go around the sun, and there's a solar system, and then we realized that there are stars that are a long way away, and then we realized we're in this island universe called a Milky Way galaxy, and then we realized this Milky Way galaxy was just one of billions of Milky Way galaxies in a universe that is expanding, and turns out it's expanding at an increasing rate. So one of the theories, which is dubbed dark energy, one of the theories is that we live in a multiverse, that there are other bubble universes out there that we'll never be able to see, but they influence or they have an effect on our universe and causing it to expand at an increasing rate. So there you go, there's a nice theory. We're not the only universe.